Here are the top 10 most important things to know about logarithms. Must know number 1. What is a logarithm? A logarithmic function has two main components. It has a base and it has an argument. This subscript b is what we call the base of the logarithm, and this x is the argument of the logarithm. And when reading this, we pronounce this as log base b of x. Now, what does this function do? Well, a logarithm is a function that gives the exponent to which a fixed number, the base, must be raised to produce a given number, the argument. Now let me give you a couple logarithmic expressions to help you understand what this function does. Let's say we have log base 3 of 9. What this function means, it means what exponent goes on 3 to make it equal to 9. 3 to what exponent equals 9? Well, 3 squared is 9. So the answer to this logarithm is 2, because 3 raised to a power of 2 is equal to 9. Let's try another one. How about log base 2 of 8? That just means what exponent goes on 2 to equal 8. Well, I know 2 to the power of 3 equals 8, so the value of that logarithm is 3. Now let's do one more. What if we have log base 2 of 1 over 8? Since we're trying to figure out what exponent goes on 2 to make it equal to 1 over 8, rewriting 1 over 8 as a power of 2 will make the answer obvious. So I could rewrite this as log base 2 of 1 over, I can change that 8 to a 2 cubed. And now I can take this power of 2 cubed and move it up to the numerator if I change the sign of the exponent. And now it should be obvious the answer to this expression is negative 3. Right, this is the exponent that goes on the base of the logarithm to make it equal to the argument. Now before I move on, you should know about two very special logarithms: the common logarithm and the natural logarithm. The common logarithm is a logarithm that has a base of 10. So if you have log base 10 of x, you don't actually have to write the base. You could just write log of x. And if you don't see a base, it's implied that the base is 10. The natural logarithm is actually a logarithm that has a base of e, which is Euler's number, that approximately 2.7 value. If you have a log where the base is e, you can communicate that instead of writing log base e, you can just write ln, which stands for the natural logarithm of x. So if you see either of these expressions, you have to know they're actually equal to those logarithms. If you were asked to evaluate log of 100, you'd have to know that even though you don't see a base on that logarithm, the base there is 10 because it's the common logarithm. So this expression means what exponent goes on 10 to make it equal 100. Well, 10 squared is 100, so the value of that logarithm is 2. Must know number 2. Converting between exponential and logarithmic equations. Let's start by looking at if we have a logarithmic equation, how could you convert that to an equivalent exponential equation? Well, a logarithmic equation typically looks like y equals log base b of x. And remember, what does this equation mean? So since y is the answer to this logarithm, I know that y is the exponent that goes on b to equal x. So using that logic, I could rewrite this in exponential form as b to the power of y is equal to x. So let's practice that with a couple examples. What if we have the logarithmic equation 5 equals log base 2 of 32? Well, what does this equation mean? It means that 2 to the power of 5 is equal to 32. So in exponential form, this equation would look like 2 to the power of 5 equals 32. What about the equation 2 equals log base 7 of, let's use a variable this time, x? Rewriting this in exponential form, well, I know that this equation tells me that 7 to the power of 2 is equal to x. So in exponential form, that's how it would look. 7 to the power of 2 equals x. So now that you can go in this direction, from logarithmic to exponential form, let's make sure you can go the other way, from an exponential equation to a logarithmic equation, to an equivalent logarithmic equation. So let's say we had an exponential equation, b to the power of m equals n. And I wanted to write that as an equivalent logarithmic equation. Well, I know the exponent is the answer to a logarithmic expression, so I'll set my equation equal to the exponent, so m equals, and since m is the exponent on b, I'll make b the base of my logarithm. The base of the power becomes the base of the logarithm, and since b to the power of m is equal to n, I know that n is the argument of my logarithm. Let's say we have the exponential equation 4 cubed equals 64. The equivalent logarithmic equation, the exponent is the answer to the log, so 3 equals log, the base of the power becomes the base of the log, so it becomes log base 4 of 64. Both of these expressions communicate the exact same information, that 4 to the power of 3 equals 64. Must know number 3, the graph of a log function. This is going to be very important to understand so that you understand the restrictions of a log function. Let's start by picking a log function that we want to graph. How about y equals log base 2 of x? And when picking points for a log function, it's actually easier if we pick values for y and then calculate their corresponding values of x. And that's because if I rewrite this logarithmic equation in exponential form, I know that this equation tells me that y is the exponent that goes on 2 to equal x. So I could rewrite it as 2 to the power of y equals x. So I'll pick some values for y. I'll just pick values from -2 to 2. And then I can calculate the value of x just by taking those y's, subbing them into this exponential equation, and get the corresponding value of x. Let me plot these points so we can get a general idea of what the function looks like, and then I'll tell you a couple of its properties. Now, before I connect these points, notice this function has a vertical asymptote at x equals 0. So I'll draw that in on our function here. Notice as this function approaches the vertical asymptote from the right side of it, the value of the function starts to go towards negative infinity. That's why there's a vertical asymptote at x equals 0. So let me actually make a comment about the domain of this function. The domain just means what values can x be in the equation, or graphically, horizontally, where does this function exist? Well, the function only exists at x values bigger than 0. So that means this expression will only have an answer when the argument is bigger than 0. So for the domain, I could say x could be any real number, given x is greater than 0. Before I move on, let me tell you about a couple general rules for log base b of x. The first rule I want to tell you about is about the argument of the logarithm. When we looked at this function log base 2 of x, we saw it only existed when x was bigger than 0. So we now know that the argument of a logarithm always has to be bigger than 0. So I could say that x, which is the argument of the log, has to be bigger than 0. And it's easiest to understand that when I give you a counterexample. So what if I gave you a log expression where the argument was not bigger than 0? What if I gave you the expression log base 5 of -25 and asked you to find the value? Well, that would mean what exponent can I put on 5 to make it equal to -25? It doesn't matter what exponent you put on a positive number. It's never going to become negative. And the other property you have to know is about the base of the logarithm. Notice when I chose the base of this function we analyzed, I made it a positive number. And that always has to be the case. The base of a logarithm has to be bigger than 0. And once again, if I give you a counterexample, how about log base -4 of 2? That would mean what exponent can I put on -4 to make it equal 2? Well, that exponent doesn't exist. And there's another condition actually. Not only does the base have to be bigger than 0, it also cannot be 1. An example of why that can't happen, well, what if we had log base 1 of 2? That means what exponent goes on 1 to equal 2? Well, it doesn't matter what exponent you put on 1, it's always going to be equal to 1. There's no way it can get equal to 2. So for that reason, a logarithm cannot have a base of 1. Must know number 4, the power rule of logarithms. Here's the first main rule that you can use when working with a logarithmic expression. If you have log base b of a power, so of m to the power of n, there's a log rule that says that you can take the exponent of the argument and rewrite it as the coefficient of the logarithm. So this would be equal to n times log base b of m. Now this rule can only be used if the base of the log is bigger than 0 and not 1, and also if m is bigger than 0, right? Because m is the argument of the log, we know the argument of a logarithm has to be bigger than 0. Now let me show you how we could use this rule. Let's say you had the expression log base 3 of 9 to the power of 4. There's a few ways we could think of evaluating this, but it might be easy if you notice that the argument is a power. So you can take the exponent of that argument and rewrite it as the coefficient of the logarithm. So this would be equal to 4 times log base 3 of 9. And then log base 3 of 9, well, that just means what exponent goes on 3 to equal 9? 3 squared is 9, so that logarithmic expression is equal to 2. So I have 4 times 2, which is equal to 8. Let me move this and show you another example. Let's say we had log base 2 of root 8. Well, remember that square root symbol can be written as a rational exponent. It can be written as 8 to the power of 1 over 2. And now the power rule of logarithms tells me I can take that exponent of the argument and rewrite it as the coefficient of the logarithm. And log base 2 of 8 just means what exponent goes on 2 to make it equal to 8. 2 to the power of 3 is 8, so I know that logarithmic expression is equal to 3. And a half times 3 is 1.5, or 3 over 2. This power rule of logarithms is also useful for solving different types of equations. Let me give you a couple equations that we could use this rule to help solve. The first one is the equation 2 equals log of 3 to the power of x. Since this x is the exponent of the argument of a logarithm, I can write it as the coefficient of the logarithm. And then I could just divide both sides by log 3. And if I use my calculator to get an approximate value for that, it's about 4.19. A second example where the power rule of logarithms would come in handy would be the equation 100 equals 2 to the power of y. Now there's a couple ways we could solve this equation, but one way would be to take the logarithm of both sides, and then to use the power rule of logarithms to take that exponent of the argument and write it as the coefficient of the log. And then also notice log 100, well, that's the common logarithm. The base of the log, even though we don't see anything there, is 10. So that means 10 to what exponent is 100? Well, 10 squared is 100, so the answer to that log is 2. So I have 2 equals y times log 2. I could divide both sides by log 2 to get y equals 2 divided by log 2. And then using a calculator, I could get an approximate value for that of 6.64. Must know number 5. The product and quotient rules of logarithms. Let's start with the product rule of logarithms. The product rule of logarithms tells me that if you are adding two logarithms that have the exact same base, so log base b of m plus log base b of, let's say, n, you could rewrite the sum of those two logarithms as a single logarithm if you keep that same base b, but multiply the arguments together. So m times n. Now when using this rule, you have to be careful. It can only be used when, of course, the base of the logarithm is greater than 0 and not 1, but also when the arguments of the logarithms are greater than 0. So let me show you two examples of how we can use this product rule of logarithms. Let's say we had log base 3 of 7 plus log base 3 of 5. Because we have two logs being added, and each of those logarithms have the same base, those can be rewritten as a single logarithm by keeping that same base of 3 and multiplying their arguments, 7 times 5. And 7 times 5 is 35. And let's do one more. This time, let me make it a bit more difficult. I've got 2 log 5 plus a half log 16. Now, in the product rule, notice the coefficients of the logarithms are all 1. And in this example, they're not 1. So we have to take care of that by doing the power rule of logarithms, which tells me I can take each of those coefficients and write them as the exponents on the arguments. So this would be equal to log of 5 squared, which is 25, plus log of 16 to the half. 16 to the half just means root 16, which is 4. And now I could combine these as a single logarithm. Because they're logs being added to have the same base, right? The base of both of these common logarithms is 10. So I could combine them as a single log by keeping that base of 10 and multiplying the arguments. 25 times 4. And 25 times 4 is 100. And this would be easy to actually fully evaluate. Log 100 means what exponent goes on 10 to get 100? That's 2. The second rule for this section is the quotient rule of logarithms. The quotient rule states that if you have two logarithms being subtracted, so log base b of m minus log base b of n, as long as the bases of those logarithms are the same, we could rewrite those two as a single logarithm with that same base by dividing the arguments. So m divided by n. And once again, this rule can only be used as long as the base of the logarithm is bigger than 0, not equal to 1, and the arguments of both of the logs are bigger than 0. And now let me give you a quick example of how this can be used. Let's say you had log base 4 of 30 minus log base 4 of 6. Two logs being subtracted where the logs have the same base. You can use the quotient rule, which says keep the base the same and divide their arguments. 30 divided by 6, that's 5. And this expression means what exponent goes on 4 to equal 5. So it's 1 point something. You could use your calculator to get an approximate value. It's about 1.16. Must know number 6, other rules and tricks. Let me show you a few other rules that are going to be helpful when working with logarithms. And before I show you the rules, let me remind you about the restrictions on a logarithmic expression. The base of the logarithm has to be bigger than 0 and not 1, and the argument of the logarithm has to be bigger than 0. The first rule I want to show you is the change of base formula, which allows you to change the base of any logarithm. So if we have log base b of m, and we want to change the base from b to some other number, we can do that by writing it as a quotient of two logarithms with that new base that we want. So I could rewrite log base b of m as log base a of m over log base a of b, where this a could be any number bigger than 0 and not 1. So let me show you how this formula works. Let's say you had log base 4 of 20. You could rewrite that as a quotient of two logarithms with a new base. And most often this formula is used to change the base to 10 so it becomes the common logarithm. So this would be log base 10 of 20 divided by log base 10 of 4. So log base 4 of 20 can be rewritten as log 20 divided by log 4. That's the change of base formula. Another rule that might be useful is the rule that tells you that b to the power of log base b of m, that would just equal m. If you think about what log base b of m means, that means the exponent that goes on b to get m. So if you take that answer and put it as the exponent on b, you of course get m. So an example of how this would work is that 3 to the power of log base 3 of 9, well, that would just equal 9. This exponent, log base 3 of 9, means what exponent goes on 3 to get 9, and that's of course 2. So when you put that as the exponent on 3, 3 squared is 9. So as long as these two numbers match, then the argument is going to be the answer to this expression. And this tool is often used to rewrite a number as a power with a different base. So for example, if I wanted to rewrite 5 as a base 2 power, well, I could change this to a power of 2 if I make the exponent log base 2 of 5. And then a couple small other tips. If you have log base a of a, where the base and the argument match each other, well, that's just going to be equal to 1, because a to the power of 1 is equal to a. So an example of this would be if you had log base 5 of 5. That means what exponent goes on 5 to get 5? That's 1. And another small rule, log base b of 1. Well, anytime the argument of your log is 1, we know the answer to the log is 0. For example, if you had log base 5 of 1, what does that mean? It means what exponent goes on 5 to get 1? Well, the answer to that is 0, because 5 to the power of 0 is 1. Must know number 7, solving exponential equations. Let me write 3 exponential equations, and I'll show you the different strategies you can use to solve them. If we look at the first equation on the left, notice all we're trying to figure out is what exponent goes on 2 to equal 20. Well, we can just convert this to a logarithmic equation by saying the exponent equals log base 2 of 20. This function will find the exponent that goes on 2 to get 20. It's going to be 4 point something. To find an approximate value, you can either type it like that, but if your calculator is not able to change the base, you can use the change of base formula to convert this as a quotient of common logarithms. So we could write that as log 20 divided by log 2. And it's about 4.32. The next equation, notice we have 2 terms that have a variable in the exponent. When that's the case, when you have a power equals a power, try and rewrite the power so they have the same base. So I would rewrite that 8 as a base 2 power. I can change the 8 to a 2 cubed. And then using exponent rules, I know I can multiply that 3 by that 2x minus 5. 3 times 2x minus 5 would be 6x minus 15. And once you have power equal power where the bases are the same, the only way this equation could be true is if the exponents were equal to each other. So you can just set the exponents equal, x equals 6x minus 15, and then solve this by rearranging. And then the last exponential equation looks very similar to the middle one, where we have a power equal to a power, but it would not be easy to rewrite them with the same base. So what we do instead is we take the common logarithm of both sides, and then use the power rule of logarithms, which tells you you can take the exponents of the arguments and write them as the coefficients of the logarithms. On the right side of the equation, we can do 2x minus 5 times log 7 by multiplying log 7 by both the 2x and the negative 5. And then I'll rearrange this equation to get the terms that have an x to the same side of the equation. A couple things to do here. I could simplify this expression by taking this coefficient of 5 and writing it as the exponent on the argument. 7 to the power of 5 is 16,807. And on the right side of this equation, I notice both terms have an x, so I'll common factor out an x. And then this factor, I can simplify. I'll move the 2 as the exponent on the 7 to make it 7 squared, which is 49. And then when subtracting logs with the same base, you can write it as a single log by dividing the arguments. So that would become log 49 divided by 2. I'll make a bit more room. And my last step to isolate the x is to divide both sides by log of 49 over 2. And then using the change of base formula, I could rewrite that as a single logarithm. I could write it as log base 49 over 2 of 16,807. That's the exact value of this answer. Using a calculator, you could get an approximate value of about 3.04. Must know number 8, solving logarithmic equations. Let me write 3 log equations to solve. Let's look at the first equation. One general strategy when solving a log equation is to get the equation to be in the format log equals log. Because if we have 2 logs equal to each other, where the bases are the same, then you know that the arguments must be equal to each other. So this equation looks like it's already almost in that format. If we take this coefficient of 2 and write it as the exponent on the argument, then that would make this equation easier to solve. So I'll write this as log of x plus 5 equals log of x minus 1 squared. And now that we have 2 log expressions equal to each other, where the bases of those logs are the same, the bases are both 10, I know the only way this equation would be true is if the arguments were equal to each other. So I can say that x plus 5 would have to equal x minus 1 squared. And now this is just a quadratic equation to solve. Let me expand the right side. X minus 1 squared. We do x minus 1 times another x minus 1. That would be x squared minus 2x plus 1. Rearrange this to set it equal to 0. And then I can factor this quadratic by finding numbers that multiply to -4 and add to -3. The numbers that satisfy that product and sum are x minus 4 and x plus 1. Using the zero product rule, I know the product of these two factors would be 0 if either of the factors would be 0. This factor would be 0 if x was 4, and this factor would be 0 if x was -1. So my solutions to this equation are x equals 4 and x equals -1. Now we have to be careful when solving logarithmic equations. Sometimes you might generate what's called an extraneous solution, which means a solution that might work for many of the equations throughout our process, but does not work for the original equation. And when we use log rules, remember the restriction we have for logarithms is that the argument of a logarithm has to be bigger than 0. So we need to check both of our solutions and make sure they don't make any of our logarithmic expressions become undefined. Make sure it makes the arguments of both our log expressions be greater than 0. 4 subbed in for both of the x's in my log expressions, well, it would make that argument 9 and this argument 3. Those are both greater than 0, so that's fine. But if I sub in -1, it makes this argument 4, but it makes this argument -2. So this answer of -1 makes this log expression undefined, which means it cannot be an answer to this equation. So we actually have to reject that answer and say that's an extraneous solution. The only answer to this equation is 4. Now the fact that this makes both of these arguments positive doesn't guarantee it's the right answer. You should also take the time and make sure that when you sub it in for the x's, it makes the whole left side equal to the whole right side. This middle equation is in a format that if we convert this to exponential form, it's very easy to solve. So if you have a logarithm equals a constant, just convert to exponential form. This log expression means that 2 is the exponent that goes on 5 to equal 2x minus 3. So I can write that. And now just solve this linear equation. Add the 3 to the left side, and then divide the 2, and you get x equals 14. Checking this answer in the original log expression, it makes the argument here be positive. And if we actually evaluate the whole left side by subbing 14 in for x, we get log base 5 of 25, which is 2. So 14 is the right answer. And the last log equation, I see two terms that have an x, so let's get them on the same side of the equation. So I'll take this negative log, add it to the other side. And now two logs being added, where the logs have the same base, I can use the product rule to combine those as a single logarithm by multiplying the arguments. Multiplying the arguments gives me x squared plus 9x plus 18. Now that it's a log equals a constant, let's convert it to exponential form. Remember, on the left, we have the common logarithm, so the base is 10. So that equation means that 10 to the power of 1 is equal to the argument. It's a quadratic, so I'll set it to 0 before solving further. And then that's factorable. The numbers that multiply to 8 and add to 9 are 8 and 1. So the solutions to this equation are x equals -8 and x equals -1. This answer of x being -1 makes that argument positive 5, makes that argument positive 2. So because both those arguments are bigger than 0, that is probably a fine answer. You should also double check and make sure it makes the whole left side equal to the whole right side. But if you sub -8 in for the x in the original equation, it actually makes both of these arguments be negative. So it makes both of those expressions undefined, so it cannot be an answer to this equation. So x equals -8 is an extraneous solution. So the only answer to this equation is x equals -1. Must know number 9. What are logarithms used for? There are two main things I want to show you. The first of which is that logarithms can be used to help analyze very small or very large numbers. For example, let me give you a set of values. I'll start with very small numbers like 0.0001, and then I'll increase by factors of 10 until I get up to some very large numbers. So let me just continue this table. So you can see at the extremes of this table, I've got some really small numbers at that end and some really big numbers at this end. So if I were to take each of these numbers and do the log of each of these numbers, so I'll take all of those numbers and put them as the input into this log. And then let's look at what is this logarithm output. If I take this first number